Uh, and I wanted to start with let me pass out this worksheet, but I want to do the first one together because it's a good kind of way to practice what might be too difficult of a question at the beginning. For those of you who are on Zoom, I guess I should. For those of you who are on Zoom, it should be posted, I believe, under Friday. And it has a picture of a pulley on it, as you can see. So try to find that worksheet. I can't remember what I had posted for Friday, but I believe this is one of them. So we're going to try to use our result that the sum of the torques equals I alpha. Remember, this is our F equals ma for rotational motion. Torques are like forces, but for rotation, they tend to get things rotating. The bigger the torque, the easier it is to get something rotating. I, the moment of inertia, is like the mass, but for rotations, how hard it is to get something rotating. And alpha is the analogy to acceleration. Where's my torque net equals I alpha? Yeah, so torque net equals I alpha. That means if you sum up all the torques on something, that's equal to the moment of inertia times alpha. Now, what makes this problem a little bit more difficult, not sure why I'm starting with a more difficult one, but it'll be a good thing to sort of explain, is that we have two pieces that are connected. So the idea is we've got a uniform cylinder, so sort of like a solid disk that's pivoted to rotate about the very center. So you can see the dot at the middle of the disk. It's supposed to be a frictionless pivot, so there's no grinding at that axis. It can freely rotate. And yet, this cylinder right here has a significant moment of inertia. That means it doesn't immediately rotate one way or the other, but you have to sort of work to get it going or apply a torque for a period of time to get it going. So we wound a string around it a couple of times, and then we let the string hang off the edge. Well, there's something holding it up, a little pin right there with no friction. And then we've hung a mass to it. And of course, the mass is going to fall. And meanwhile, this thing's going to speed up, right? And the mass is not going to be able to fall at free fall. It's going to fall at some smaller rate of acceleration because this thing sort of resists getting rotating because it's got a moment of inertia. Okay, so 2 kilogram mass is the mass of this. It's a 20 centimeter radius. Oh, I'm sorry, I didn't read the problem carefully. There is a friction force at the axle, which creates a torque in the direction opposite the rotation. And does it tell us about the torque? Nothing about the torque in here. Should tell us about the torque. Oh, maybe it's different in your version. When I'm looking at mine here, it does tell us about the torque, but your printed version, it doesn't. In my version, it says it exerts a torque of 1.1 Newton meters. Okay. Maybe I better go to the board here. So let's adjust things. Looks like this is showing the board just fine. Oh, and I didn't bring my pens today, so I'm stuck with one pen. Let's hope this is a pen that works well. That's not very hopeful. Since I brought this cart today, I didn't bring my normal selection of pens. All right, so we've got, let me try to draw what we know about this. So here is a uniform cylinder that we can wind some string around. It's got a radius of 0.2 meters. Okay, and it's got a mass of 2 kilograms. We've wound some string around it, and the light string, the mass of the string is negligible, and then we've hung a mass which is 0.5 kilograms off the end of it. And I don't know why I put this friction force in there, but there's some, there's a little bit of grinding in this pin that's holding this thing, right? It can't rotate completely freely, or it's not well lubricated where that pin is holding this thing up. And what that means is as it is unwinding and spinning faster and faster in this direction, there's going to be a frictional torque which is trying to twist it in the opposite direction. Okay, so in this case, the frictional torque, I might write that as tau frictional, is equal to, in my printed version here, which is different than yours. I must have grabbed the wrong version when I printed out yours. 1.1 Newton meters of frictional torque. So that means there's torque that's trying to twist it back opposite the direction that it's rotating, always with that magnitude, okay? And the question is, what is the magnitude of the angular acceleration of the pulley? This thing's going to start rotating faster and faster. Apparently, there's going to be a constant angular acceleration. The question is, what is it? We've really got two pieces that are interacting here, right? The pulley and the falling block. And we're going to, just like when we were using Atwood's machine before, we separately analyzed the two blocks that were hanging over the pulley. Here, we're going to separately write down F equals ma for this block and torque net equals I alpha for this cylinder. And we're going to write down a system of equations. And just like we had to be careful in that case of choosing a consistent positive direction so that when one is moving positive, the other one's moving positive, I have to do the same thing for this and this. In other words, I know this is going to go down when I release it from rest. So let's call this, positive, I don't know what, y. We'll just call it the positive direction for when I'm doing F net equals ma. If that's positive, then unless I want to get horribly confused and probably get it wrong, I'm going to also choose this to be the positive direction so that when this moves in the positive direction, this rotates in the positive direction. So this is going to be my chosen consistent set of positive directions. And now all I'm going to do is write down F net equals ma for this and torque net equals I alpha for this. So for this one, if I were to do a free body diagram, it's not very exciting. I have 0.5 kilograms there. So there's a force going down, mg, 0.5 times 9.8. And I've got a tension. I don't know what that tension T is in the string. So I've got an unknown tension going up. I'm just going to write that as T. And if I write down the sum of the forces equals ma for, this positive component direction here, let's call it plus x. Sum of the force x components equals max. Okay, this one comes in with a plus sign for my positive chosen direction. 0.5 times 9.8. The t comes in with a minus sign. The mass of the object in the free body diagram is 0.5 kilograms. And ax, I also don't know. So that's good, of course, not surprisingly, we haven't done anything having to do with the cylinder yet. I'm not going to be able to solve anything in this problem right away because I need to involve the cylinder. There are two unknowns in this equation. We don't want to know t. You might not be surprised that ax is not too different than the angular acceleration. We'll be able to relate it to that one. Okay, now let's focus on the pulley, again, with the positive direction going that way. What are the forces that are being exerted on the pulley? Here's where I really wish I had a different color pen, but I don't, unfortunately. What are the forces that are being exerted on it? Well, of course, gravity is pulling down on it all over the place. Now it's a uniform. Oh, thank you so much. Let me try to draw. And they're all like Easter pastel colors. That's kind of nice. Let me try to draw the forces that are on here. Of course, if the pin, there's a pin in the middle. If the pin weren't pushing up on it, it would start falling down. So whatever it's rotating on, that little rotation pin, is exerting a force up, right? So I've got some F pin going up. Of course, gravity is pulling on it all over this uniform cylinder. But we said last time that we could simplify it and say, as long as I know where the center of mass of the cylinder is, I could pretend that the entire mass of the cylinder is located at the center of mass, and that all of the gravitational pull is being exerted from there. Where is the center of mass of this cylinder? Yeah, it's at the center. As I promised you, anytime you have a uniform object, it's always going to be at the center of symmetry. So the center of symmetry of this is right where the pin is. So, I'm just going to write it notionally, mg going down. There's another force. We can pretend that it's all being exerted there, even though I know it's distributed over little bits of mass all over the whole thing. What other forces are being exerted on this? Well, the tension is sort of pulling down from the very edge. So it's as if, again, just drawing it as forces being exerted on the cylinder. Whatever the tension is, it's as if right where this string attaches to the edge of the cylinder when it starts wrapping around, that's where that force is being exerted straight down. It's as if I'm pushing on that point, the direction straight down. And then I don't really know how to draw the torque due to friction, but since this thing is going to be rotating in this direction, we're going to get a negative torque due to friction in addition. Okay, so let's try to write that over here. The sum of the torques about that rotation axis is equal to the moment of inertia of this times the resulting angular acceleration, and it's that angular acceleration that I'm hoping to find here. Okay, so in this case, what is so I'm calculating torques with respect to this axis. Can anybody help me figure out, if I knew the force due to the pin, how much of a torque would it be exerting about the axis of rotation right at the center? Let me just ask your intuition. Okay, this thing's pivoted to rotate at the center. What do you think? The pin is pushing up at the very center. Is it trying to rotate it one way or the other way? No, the pin, by pushing up at the very center, is not trying to rotate it in one way or the other. If the pin were pushing up over here, then it would be trying to rotate it in one way or the other. Another way to think about it, so let's just think of a separate problem, back to when we first talked about torque. If I said, here's the center of rotation, and I apply a force here, that force is trying to rotate it in that direction. And the relevant moment arm would be, our rule for getting moment arms is, you draw the line that contains the force, and you find that perpendicular direction. And it's just force times moment arm. Now for this force, what's the moment arm? If I draw the line that contains the force from the pin, and I find the perpendicular distance from that line to the axis of rotation, what is that distance? It's 0, right? Because the force is actually along a line that goes right through the axis of rotation. So you can think of, for this force, and of course for this force, they're not exerting any torques. One way to explain that is because the moment arm is 0. Another way, just more intuitively, is it's not trying to rotate it one way or the other, right? Those two forces, if you apply a force right at the pin, or even up here, you wouldn't be trying to rotate it in one way or the other. So the pin force gives 0 torque. I'm just going to write that as a 0. The weight force gives a 0. What about the tension force? Is it exerting a torque about the center? Sure, if you attach a rope there and you pull down, it's going to try to make the thing rotate, right, in this direction. So how do I figure out what the moment arm, right, is? I don't know what the tension is, but we've got a symbol for it, right? It's T. Let me draw the line that contains it. The moment arm is the distance from that line that contains the force we're concerned with to the axis of rotation. So I'm just doing force times moment arm. First of all, is it a positive or negative torque in my convention? It's positive, right? Remember we said, just use your intuition. If it's trying to rotate it in the positive rotation direction, that's a positive torque. So this is going to come in with a plus sign. The magnitude of the force is the tension. Tension is a force, right? That's how hard it's pulling it on the end of the string. times the moment arm. And the moment arm is just the radius of the cylinder, right? 0.2 meters in this case. Okay, that's a non-zero torque. And then I've got to add in the frictional torque. Not surprisingly, if it's rotating in the positive direction, frictional torque is going to be negative because it's trying to twist it back or hold it back. So the frictional torque, we were just told in SI units, is 1.1. So that's the sum of all my torques. You didn't really have to write down the 0 plus 0, but okay, and that's equal to the moment of inertia of this thing. Am I running out of space there? We got a little bit of space left. Moment of inertia. Let's go back to our table of moments of inertia. We've got a uniform disk. A uniform disk looks like this, right? Something that I could wind the string around. And in fact, sometimes people say it's a uniform disk or a uniform cylinder. A disk is just a very thin cylinder, right? If we think of a flat circle, that's still a cylinder. It's just a cylinder that has a very small height. In this case, we're assuming it's some kind of cylinder or disk. So let's see if we can find, here we go. There's our moments of inertia. So we're talking about a solid cylinder or disk, which is rotating about its symmetry axis. That's the case we have there. So the moment of inertia is 1/2 mr squared, where m is the mass and r is the radius. Why do I have Hunter? Let's see, how do I unpin? Remove pin. There we go. That's what I want. Okay, so that's equal to I, which we just found out was 1/2 times the mass of the cylinder, 2 kilograms, times the radius of the cylinder, 0.2 squared. And now it looks like I'm just about out of space here. Let me rotate this a little bit, so we don't really need to see the screen. That's I times alpha. And alpha is what I want to find here. Okay, so there's my second equation. I'll just leave out the zeros. The only unfortunate thing is that instead of being at 2 equations in 2 unknowns, we would know how to solve that. We've got 2 equations in 3 unknowns because I've got an alpha here and an AX there. But we can relate those two. And in fact, I can trade out this AX for an alpha using our relationship between linear quantities and angular quantities that we talked about a little bit earlier. We said that one of the things that was derived was that the tangential acceleration of a point on something that's spinning, right? So I can think of this point right here, it's spinning around. Its tangential acceleration, which is the component of acceleration along that direction, is equal to r times alpha, where r is the distance of that point from the axis of rotation and alpha is the angular acceleration. And I want to trade out this AX for the alpha. So the idea is AX is the acceleration of this block, how fast it's accelerating downward, right? How fast it's accelerating downward is the same as the tangential component of the acceleration of this one, right? It's how fast it's accelerating in that direction. That's the same as how fast this is accelerating in that direction. It's just that because this one's moving in a circle, it's also accelerating towards the center. We don't care about that right now. Okay, so in this case, A tangential is the same thing as what we're calling AX. So AX equals R alpha. So I can replace this AX, I'm just going to erase it there with an R times alpha. Oh, and I know R, right? R is 0.2 meters. 0.5 times 0.2 times alpha. And now I've got 2 equations in 2 unknowns, and I want to solve for alpha. And to do that, of course, what I'd first do is solve for t, right? I could solve, this one's got a minus t here. I could add it to both sides and subtract that off and get t equals in terms of alpha, and then substitute over here for t. So let's do that. This equation here says that t is equal to 0.5 times 9.8 minus 0.5 times 0.2 times alpha. And I'm going to substitute that into this equation up here, all for t. So I can replace t with 0.5 times 9.8 minus 0.5 times 0.2 times alpha. All of that is t. It needs to get multiplied by 0.2. Subtract off 1.1, and that's equal to, well, let's see, the 1/2 and the 2 cancel out. That's equal to 0.2 squared times alpha. And now I can solve for alpha, right? It's just a little bit of algebra, right? I'm going to put all my multiply this out, put all the alphas on one side, and divide out whatever the coefficient of alpha is. All right, let's go back to the slides here. Is there another question? There is a question. It looks like a kinematics question, but let me just flip through it again. Well, I guess my version on here is a little bit messier, but here's my F net equals ma equation. T expressed in terms of alpha after I traded out an alpha for an A for an alpha. Torque net equals I alpha. And it looks like I've forgotten about this friction force. Yeah, there is a friction force in your version. It should say 1.1 Newton meters. Clearly, I need to retype this one because it's a little bit wacky. But I wouldn't trust this number right here because it looks like the 1.1 didn't come into my solution. But the idea is I'm eliminating the t in favor of alpha, and then I get an equation that's just in terms of alpha, and I can solve for alpha equals. I'm betting that this is incorrect here because it looks like that friction force is not taken into account. If I were to redesign this, I would probably leave out the friction force, just making it needlessly complicated for the first time we've done one of these problems. But you know, this, for a problem that involves two connected things and involves rotational inertia, this is about as easy as they come. Now, I would also, just to reassure you, say that this is probably the very hardest of this kind of problem that you would ever likely see on an exam, because, you know, you could say, well, what else could we do? Well, we could make an Atwood's machine where not only do I hang a mass on this side, but I hang another mass on this side, but there's a massive pulley in between. Then I'm going to have 3 equations and 3 unknowns. The tensions on the 2 sides aren't necessarily going to be equal anymore. You remember earlier on when we were talking about massless, frictionless pulleys, we said in that case, the tensions match. But if you got a massless, if you've got a massive barbell kind of plate, right? And you can imagine a situation where you've got, I think I made this analogy at the beginning, right? So I've got massive barbell plate. I hang a little piece of styrofoam over here. And over here, I hang a pretty massive 2-kilogram mass. Nobody believes that the tensions in those strings are going to be the same in this case, right? If it were truly a massless, frictionless pulley, then yes, they're going to match up at every instant. But as soon as this thing has some rotational inertia or moment of inertia that's not negligible, then you need a different tension on this side than you have on this side. Okay. So the second question on here is, if the mass is released from rest, how long does it take the mass to fall 1.5 meters? Let's just finish up that question together. How would I use, given that I've found alpha, how could I use that to answer the second question? If the mass is released from rest, how long does it take it to fall 1.5 meters? So I'm not going to claim that I have the correct number here. But let's assume that we've solved for alpha. How could I use that to figure out how long it's going to take to fall 0.5 meter? 1.5 meters. What do you need to make that an easy question that we could have done back before exam 1? Yeah, and to do kinematics, I need to know what the acceleration of this is. Now, what I found is the angular acceleration of this. Do we know any principle that will allow us to translate that into the linear acceleration of this? Yeah. Yeah, we already talked about the fact that, you know, the tangential acceleration is the same thing as the linear tangential acceleration of the point on the edge of the wheel is the same as the linear acceleration of this. So I can calculate AX for the half kilogram one by R times alpha, where R is the radius of that disk. And then once I've got AX, I'm just going to do kinematics. Assuming that's on here, I'm not going to do it at the board, but the mass is released from rest. How long does it take for the mass to fall 1.5 meters? Calculate, well, I called it AY here, and then use that in a kinematics equation that says, I have a T, or I want to know a T, and I have the distance that is going to fall 1.5 meters. Solve for T. Okay, I know that was probably mixing 3 new things that we've done together all at once. The really new piece that we hadn't talked about before was coupling together a rotating thing and a linearly moving thing in a kind of pulley system. But we're also using torque net equals I alpha, which we hadn't really practiced with before, and throwing in our relation between linear and angular quantities over there. You know, there's probably at least one homework problem that has to do with where you have to write down a system of equations like that. So just keep that in mind. Let's look at a second one, and maybe this should have been the first one because I think it will end up being quite a bit simpler. A uniform rod of mass 2 kilograms, wow, and length 1 meter. It's not your average meter stick because it weighs 2 kilograms. Oh, and I forgot I brought something to pass around. Speaking of uniform rods, here's a pretty hefty piece of steel, pretty uniform. Just pass it around and try with your own hand to rotate it like this versus at one end. See how hard it is to angularly accelerate it and get it to moving. You probably have the intuition that it's going to be much easier to rotate like this, but we saw in our table of moments of inertia, this moment of inertia for rotation about the center was 1/4 the moment of inertia for rotation about the end. So you should find that it requires a much greater torque to get it moving with the same angular acceleration when you're holding it at the end. So you can try that and pass it around. All right, so here we've got a rod of length 1 meter. Maybe it's made of steel because it's pretty massive, 2 kilograms. Pivots freely about its left end. So we put a little pin at the left end. There's no friction in this problem. It's released from rest in a horizontal position. So we've got it horizontally oriented like this with the pin over here, and we just let go of the one end. And of course, it swings down like that. And the question is, as it's passing that point 30 degrees below the horizontal, what's its angular acceleration at that point? And in fact, we're going to find out the angular acceleration changes the whole way you go down. It's not the same all the way down, but the angular acceleration is changing as you go down, but we're just supposed to find that one point. Think about this for a minute. Use torque net equals I alpha. We want to find alpha at the point that's pictured. How are you going to calculate torque net? And let me bring up the table of moments of inertia so that you can see. This is on the back side of the sheet that I've handed out. Let me go back to my table of moments of inertia. Here it is. Rod about one end is 1/3 ml squared, where L is the length of the rod. So here L is 1 meter. Everybody done with that? Okay, there's actually not that much work to be done on this one. But probably really should have been the first one on the worksheet, but I want to know how, this is a rigid body rotating about a fixed axis. So it's the kind of thing we've been talking about. It's not shaped like a disc, but it happens to be a rod rotating about one end. And I want to know the rate at which its angular velocity is increasing as it passes by this location right there. Okay, and of course, what we have to work with is the sum of the torques about this axis. That means I have to look at all forces that are acting on this and figure out what torques they translate into. And that's equal to the moment of inertia of this thing times its resulting angular acceleration. You know, I wasn't really thinking about signs here, but you know, it's going to be angularly accelerating in this direction. So let's just call the direction it's speeding up in the positive direction. I think I was thinking of the magnitude of the angular acceleration. Okay, so what forces are being exerted on this rod? I see two. Gravity, certainly. Now, gravity is a little bit complicated because gravity is being exerted on all the little bits of mass all the way along here. Why isn't that a problem for me? Sounds complicated, right? I got a little bit of a force going down here, a little bit of a force going down here, lots of different forces. Austin? Yeah, we can fictionally pretend, we already justified this, that this is actually, there's no approximation here. It's exactly going to be the same result for the torque of all these little bits of forces if we pretend that at the center of mass, which at this is a nice symmetric, so it's right at the center of symmetry of it at the half-meter mark, we can pretend that the entire mass is located there and the resulting force generates the torque. That's not true. The force is distributed all along it, but we'll get the same torque we already justified if we just pretend all the mass is concentrated right there. Okay, so one of the torques we have, let's see, is that a positive or a negative torque in my convention? Positive, right? It's trying to twist it in the positive direction. And so my torque is going to come in with a plus sign. And well, I have three choices. I can either use F perpendicular times R, or R perpendicular times F, or FR sine theta. Anybody see one directly that might be easier to use here? FR sine theta? Yeah, I mean, we could certainly do that. So what does R look like here? If I were to draw in that vector R, where do I draw from and to? Because in order to figure out what theta is, I got to make sure I have the right theta. This is not necessarily our theta. That's just some random angle that was given here. In order to figure out what theta is, you have to draw in R. R always points from the axis of rotation to the point at which the force is being applied. So for this force, this is a picture of what our vector R looks like. And that angle theta was defined as, you just keep going along that direction and you ask yourself, how far do you have to pivot to get to the force direction? So this angle here is defined as theta. Now, is that angle 30 degrees? It's not. It's hard to tell because I didn't make a very accurate drawing here. This might be a little bit bigger than 30 degrees, but it's not, right? I mean, if you think about it, this angle is 30 degrees. So what's theta? 60. So one way we could do it is just to say magnitude of F times the magnitude of R, and in this case, the magnitude of R is 1/2 meter, right? That's how far from the rotation axis to the center of mass, times the sine of 60 degrees, FR sine theta. Now, to me, I wouldn't have said that that's the easiest way to do it. I was thinking in terms of the magnitude of the force times the moment arm. How would I, if I wanted to try to rewrite this here, I'm just going to write it right underneath. How would I envision the moment arm for this corresponding to this force? What's the first thing we always do when we want to figure out the moment arm? Yeah, we draw the line that contains the force vector we're concerned with, right? So that's going to look like this. I can draw it forward or backwards. And then what do I do with that line that I've drawn? Sarah? Yeah, just say how far from that line to this, by which we always mean perpendicular distance, right? When I said, here's a line, how far to this point, and I told you that distance, you'd be like, what are you thinking about? It's always the shortest distance when we say the distance from a line to a point, and that's that perpendicular distance. So this is the moment arm, R perpendicular. Oh, I see. I'm sorry, Zoom folks. I see the camera's gotten out of focus. Let me just reset it here. Okay, sorry about that. And so therefore, I could also calculate this as the magnitude of the force, mg, m is just the mass of the meter stick, that's 2, times the moment arm, and the moment arm is going to be, well, this distance is 1/2 meter. So if I take 1/2 meter times the cosine of 30, 1/2 meter times the cosine of 30 degrees, I get the same thing. To me, that just popped out a little bit more than trying to figure out theta. But the sine of 60 and cosine of 30 are the same number. So we're getting the same thing either way you do it. We'll leave the sine of 60 in there. Okay, what other forces are acting on this besides gravity? Yeah, the little rotation pin up here, which way is it pushing on it? Probably upwards. What's the torque that it's exerting on this about the axis of rotation? It's 0 for the same reason as the one we just did with the pulley, right? If I were to say, the pin is pushing on, the force of the pin is, in any case, it's being applied at the pin. And therefore, the moment arm for that force is 0. How far from that line to the axis? So any force that's acting at the axis of rotation doesn't contribute a torque at all. So that's our torque net, and that's equal to I. Got to remember back for rotation about the end of this thing, it's 1/3 ml squared. So m is 2 kilograms, I think, right? 1/3 ml squared, and here we have to use the total length of this, so that would be 1 meter squared. 1/3 ml squared times alpha. So I can just calculate what alpha is. I got to put in 2 and a 9.8 there. I get alpha equals 12.73 radians per second squared. All right, how do you think that compares to, what was if I asked the question, what's the angular acceleration right after I released it? It hadn't really had enough time to fall, so it's essentially horizontal, or it's just microscopic amount below horizontal. Is that angular acceleration going to be bigger or smaller than the one we just calculated at 30 degrees below? You don't have to calculate the number. I just want to know qualitatively, is it getting smaller as it goes down, or is it getting bigger, the angular acceleration, as it drops? Smaller. You can kind of see that because, when it's rotated up here, this center of mass would have been somewhere about right there, right? Same mg going down, but a bigger moment arm, so a bigger torque. Same I, and so a bigger alpha. Bigger torque is a bigger alpha. What about, what's the angular acceleration? I mean, I let this thing drop and it's zooming by the bottom, right? So it's rotating around in that direction after I've let it go from rest. What do you think the angular acceleration is as it's passing this bottom point here? Well, we could calculate. What's your intuition about it? What do you think? It's not angularly accelerating, right? When it's over here, if you think about gravity, gravity's trying to pull it around in that direction, right? If it's over here and gravity's acting on it, gravity's trying to pull it back around that direction. So that would be a negative angular acceleration. Here we're at the point that's right in between positive and negative angular accelerations, or positive and negative torques. This is a zero torque. You can see that because center of mass is here, gravitational force would be down. What's the moment arm for that gravitational force? Zero. It goes right through the axis there. So as those things fall, we can't use angular kinematics. Angular kinematics assumes constant angular acceleration. Do we have constant angular acceleration in this case? No, angular acceleration was big, smaller, 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 zero. Then it switches sign and becomes negative as it goes to the other side. So we really can't use angular kinematics there. All right. A little practice with torque equals high alpha. Okay, let's flash forward to where we were here. All right, we're getting to the point where, you know, things are starting to pile up in chapter 8, but there's just a couple more things that we're going to learn about in chapter 8 so that we can use energy methods with rotation. Just like, you know, when we had a spring compressing, we couldn't necessarily use constant acceleration kinematics because the spring force was getting bigger and bigger, and therefore the acceleration wasn't constant. We couldn't use kinematics, or constant acceleration kinematics. Here we can't use kinematics as this thing's rotating down for the angular sense, but we still can use energy methods. So that's how we're going to solve these kinds of problems. Okay, so this is what we've been talking about. If you want to calculate a torque due to a rigid body about some axis that it's pivoted about, we're just going to pretend all the mass is concentrated at the center of mass. That's just a reminder. The next result that I want to show or justify very quickly here, because, you know, I'll show you where it comes from, but you don't need to remember where it comes from. The same thing is true about potential energy. If I've got some object that's pivoted about one end or something and it's rotating, this potential energy stored between this and the Earth is decreasing as the mass goes down. But it's a little bit complicated because this mass on this end is going way down. And this little bit of mass here is hardly going down at all. So it seems a little bit confusing. But it turns out that we can pretend that all the mass is located at the center of mass of this, wherever that is. And all we need to figure out is how far down the center of mass goes. So I want to imagine this thing rotating about that axis shown by the purple text right here. And it's going to rotate down to a lower position. I tried to just rotate it in PowerPoint there. And we're going to consider two masses, right? So here's mass M1 and mass M2 on the gray image. And then their final positions on the pink image are shown by the red ones, M1 and M2. So the change in the potential energy of this is going to be the change in the potential energy of mass M1 plus the change in potential energy of mass M2. And I got to add it up for all the masses in this thing, which is going to be a huge nightmare, right? M1 goes down by a certain amount. M2 goes down by a different amount. And that's going to be true for all of these different masses. But it seems to make sense that if I add them all up and I keep track of them, you know, maybe I divide it into 100 pieces, I would get a very good approximation for the overall change in potential energy. But let's just work on this a little bit. The first thing to realize is that there's a common factor of G in all of these terms. So let's just factor the G out in front, okay? And then I'm going to take the thing in parentheses, and I'm actually going to multiply the thing in parentheses by the total mass of this object that's pivoting around the axis and divide by it. So I haven't done anything. And I'm going to put the multiplication mass out in front with the G, and then the one that's over here is going to be combined together with this stuff. And that looks like a definition that we had before. m times y1 plus m2 times y2 plus m3 times y3 over the total mass is the definition of the y coordinate of the center of mass. And if we have deltas in front of all those, this is nothing but the change in the y coordinate of the center of mass. So the change in the potential energy is the total weight of the object times the change in the y coordinate of the center of mass, almost as if it's a point mass, right? If we said, what's the potential energy change in potential energy stored in the point mass in the Earth as the point mass goes through a change in y of center of mass, we would say, oh, it's the change in mgy. Here it's complicated, right? Lots of different masses are moving lots of different distances, but it turns out we can pretend all the mass is located at the center of mass. We know where it is. All we need to do is figure out how far down that center of mass goes and use that in the calculation. So it's a one-step thing to simplify that we've justified here. You don't have to remember the justification, but you should remember that the change in potential energy can be gotten by just pretending all the mass is located at the center of mass. You may remember in the lab on the ballistic pendulum that we used this fact, right? We found out where the center of mass was. We needed to know how far up the center of mass went to use conservation of energy. And, you know, at least in my section, we talked about how different parts of it were moving different heights. The important thing to use was the center of mass, and it wasn't really justified at the point we were doing that lab, but here's the justification for why we were finding the center of mass and why we calculated the change in the y coordinate of the center of mass. Here's another simplifying principle that, you know, again, is going to look really complicated at the face of things. As this thing is rotating around the axis, so it's spinning round and around and around, you might say, well, it's got some kinetic energy because mass is moving all over the place. Unfortunately, on the face of it, it's really complicated because the pieces of mass that are far from the axis are moving really fast, so they have a lot of kinetic energy. The ones that are close to the rotation axis are moving more slowly, so they have less kinetic energy. And it seems like to get the total kinetic energy, I have to add them all up. And in fact, you do, but when you do add them all up, it simplifies to 1/2 times I times omega squared, where omega is just the speed that it's rotating at. And notice this is an easy formula to remember because you've already remembered kinetic energy equals 1/2 mv squared. I is analogous to m. It's the rotational m version, right? Omega is analogous to v. So this is the 1/2 mv squared formula for rotation. Here's the justification, just to flash it in front of you, but you don't have to remember it, right? Here's how I would calculate the total kinetic energy. Break it up into a lot of different bits of mass. They each have their own velocity or speed. For each one of those, there's a certain distance to the rotation axis, and I can use V equals R omega for the relationship between angular and linear quantities. It's the same omega for all of these terms because there's only one rotational speed for the entire thing. So I can factor out the 1/2 on the left-hand side, and I can factor out the omega squared on the right-hand side, as I'm showing there. And what is this thing that's left in parentheses here in green? Yeah, it's the moment of inertia of this object about the axis of rotation, right? When we take the sum of all the m's times the r squared. I know it's been a long chapter and a long semester, but that is the moment of inertia in green. So what this is saying, and this is what you do need to remember, that we can calculate the kinetic energy of this object that had lots of different masses moving at lots of different speeds by just one calculation, 1/2 times I times omega squared. Okay, one more simplifying principle, and then we'll probably stop because we don't have time to do the next practice problem. We'll finish up the last example. I'm going to do a little race on Wednesday between a hoop, a sphere of the same mass, and a cylinder of the same mass, and they all have the same radius too, but they don't have the same moment of inertia. And we're going to try to predict who the winner is going to be if I let them all go from rest down a ramp. And we'll do one more worksheet problem together. Or what I thought was coming up was not coming up. Okay, we'll do this in the last 5 minutes. It's fine. Here's the same setup we had before, right? Releasing something from rest, and it is passing by this 30-degree below horizontal position. No friction there. I'm just adding on some questions here. I thought something else was coming up, but let's quickly answer these questions. We just found what the angular acceleration is at this position, but what's the rod's angular speed at this position? In other words, its omega was 0 up here. What's its omega as it's passing by this position? It's clearly not 0, right? It's sped up to some speed. How can I figure it out? Well, I can use our same old energy methods. I can take my system to be the rod plus the earth, and we'll take gravity between the rod and earth to be an internal force. The only other force that's being exerted on something that's moving is the pin force, which is upward. We'll take that to be an external force. And we're going to apply our old friend. The net work done by external forces is equal to delta KE plus delta PE. But I'm going to use my new expressions for delta KE and delta PE in terms of omegas and mg delta y center of mass. Okay, so the right-hand side, since it's a rigid body moving about a fixed axis, I'm justified in using the kinetic energy as just the single term 1/2 I omega squared. And omega initial, of course, is 0 here. I'm releasing it from rest. We're after omega final, where final means 30 degrees below the horizontal. And we can look up what I is. The only thing I need to worry about, other than, that I need to figure out how far down the center of mass moves, is how much work is done by the axis pin force. The pin force is pushing upward on it as this thing rotates down. Anybody have any intuition about how much work that force is going to do during that 30 degrees of rotation? Well, it's not going to be the opposite of the work done by gravity, because it's actually speeding up. So I know if they were both opposites, then the net work done would be 0, and that means it wouldn't change kinetic energy. But it's increasing kinetic energy as it falls down, right? It started out with 0 kinetic energy, and it's getting more and more. The key thing is that when we calculate the work done by a force, you look at when a force is being applied to an object as it moves, and we use that Fx delta x formula. The delta x is how far the point at which the force is being applied moves during the motion. How far does the point at which the force is being applied here move during that 30 degrees of rotation? It doesn't. And so the work done by the axis pin in this case is 0. Okay? So the left-hand side is going to be 0. The right-hand side, I need to figure out how far down the center of mass has moved during this 30 degrees of rotation. And that's easy. The center of mass started out up at this horizontal position, and now it's moved down here. I can draw in a little right triangle there, right? And I want to find this vertical side of the right triangle, which looks like it's going to be 0.5 times the sine of 30 degrees, right? The 30-degree angle is that one right there. And delta y, delta y is negative in this case, right? So what this is right here is a delta y in parentheses, and it's definitely going down in y. Remember, when we use mgy, we always have to take plus y to be at. Gosh, we have a lot of things building on top of each other right now. Okay, again, you got to look up in the table. This table will be given on your next exam and on the final exam. Moment of inertia of a uniform rod pivoted to rotate about one end is 1/3 ml squared. I can put in all the numbers there and solve for omega final, and you get omega final is 3.83 radians per second. And that, my friends, is all we have time for today. But I do have your test corrections. I enjoyed looking at them this weekend. I also posted finally the answers to the exam on the website. So take a look at those.